Please, Genaro, go ahead and you can start your presentation.
Okay, thank you. Okay, so I'm gonna start with the second lecture of this course. Just give me a second. Okay, so let me remind you what we saw in the previous lecture, just to have like a summary of what we saw yesterday. So we defined the ring BDR plus, BDRAM plus, as a projective limit of this ring. So we have, okay, so here I have to say that W of R is the ring of bit vectors of this other ring, which is the perfection of this ring that is not perfect. And then we inverted P, and then we took this projective limit with the powers of the kernel of theta. Okay, theta was the amorphism that we defined yesterday. I forgot to write it again here. But it was defined by taking the projection to the first component when we interpret the ring, this ring, as sequences of elements in OCP. Okay, so then after defining this ring, BDRAM plus, we defined the field, its field of fractions. Its field of fractions, which is just inverting a uniformizer T, which is, we can take it to be the logarithm of the Teichmüller-Lift of an epsilon being a sequence starting with 1, and then the pth power, the pth root of the unity, and then the pth root of the pth root, and so on. We saw yesterday, at least we stated that that series converges to a uniformizer, and well, we took that one. And yeah, so we defined the BDRAM to be that field. We saw that it is equipped with a GK invariant filtration, GK being the absolute Galois group, which is given by this. So just taking T to the power I, multiplying the ring BDRAM plus. So yeah, so we have that filtration. So before this, Rogelio in his course had defined what it was to be a B-admissible representation for an appropriate ring B. So what we are going to do, is to define some of those appropriate rings. Yesterday, the one that we defined was this one, BDR, but today we will define some others, at least 2. I mean, well, exactly 2. And yeah, so just to mention that for this ring, there's a special case, which is this one. So if X is a smooth projective variety over K, K, remember, is a p-adic field, then the étale cohomology that Felipe Saldivar is defining in his course, well, yeah, it's related to the one that he's defined there. Rogelio said in his course that this is actually a little different than the normal étale cohomology with coefficients in QP. But anyway, the thing is that is a BDRAM admissible representation. Okay. We saw that the GK invariants are exactly the K. And we made this important remark, which is actually what is going to motivate us to define some other period rings. Is this one, that the Frobenius that we have on this ring right here does not stabilize the kernel of theta. I mean, the ideal that we are using to complete here, okay? So the thing is that we are not going to get that Frobenius extended. We cannot extend that Frobenius to this ring. So in principle, we don't have Frobenius there. So that might be a problem, which is going to be fixed by defining a different or a new period ring. So before going there, let me define this. If we take a B the RAM admissible representation V, we define this Dieudonné module, D the RAM of B, as the GK invariance of this tensor product. The thing is that we can define a filtration in this Dieudonné module by using the filtration that we already have in B the RAM, that we defined right here. So basically what we are saying here is that the filtration in B the RAM induces a filtration in the Dieudonné module, associated Dieudonné module. And this gives a functor, which I'm going to denote just like this, D the RAM, from the RAM representations, I mean B the RAM admissible, which are called the RAM representations, to the filtered vector spaces. Okay, and this functor is exact, faithful, respects direct sums, tensor products, sub-objects, and quotients, duals, and symmetric and exterior powers. So basically what I'm saying here is that this functor behaves very well. Very well. I'm not going to prove this theorem. It would take a lot of time. I'm just stating that this functor behaves well in this sense. And we have this other property. If I take the RAM representation and I take the graded algebra of the Dieudonné module, I get the Dieudonné module, the Hodge state one that Rogelio defined in his course. So in particular, what we get from here is that at the RAM representation is Hodge state in particular. The proof I'm going to leave it as an exercise. It's actually a very simple exercise. If we remember a property that we saw yesterday about the graded algebra of B the RAM, which is actually just the B Hodge state. Yeah, so that's what we use to get the proof of this proposition. So the moral of this proposition is just this one. So the RAM representations are in particular Hodge state. So yeah, that we will talk about that later on. So a question that we might have right now is it possible to find a Hodge state representation that is not the RAM? So if all the RAM are Hodge state, what about the converse? So the answer is that yes, it's possible. So the converse is not true. And we will see that later. So for now, we are going to define the new period ring, which is B Cris, which I will go into the motivation maybe in the next lecture, because I should say this. Originally, I was thinking of going into detail in the construction of all the period rings of B the RAM and B Cris and the following, which is B semistable, BST. But I changed my mind a little bit by considering some questions that some of you have asked, and that I think it would be interesting for you to see with more detail, not the construction of the rings, but the geometric situations in which they are useful or they are used. And so I will dedicate more time to that, and I will spend less time defining the rings. So the definition of these new period rings, B Cris and B semi-stable, probably will not be as detailed as the one that I did yesterday for B the ramp, but at least we will have a definition, and we might discuss the details in the training sessions if you want. So yeah, let's go to the definition of B Cris, and after we will go to the definition of B semi-stable. So we will consider a generator of the kernel of theta. So yesterday, yeah, I'm sorry that I forgot to write the explicit definition, but as I said, it was just taking the first component of each coefficient in the series representation. We might take this one here with p tilde. I'm denoting an element, you know, the series, or at least one series, sequence, not series, sequence, which the first element is p. So just as epsilon is a sequence in which the first element is 1, this p tilde denotes a sequence that its first element, the first term of the sequence is p. Okay, so this is a generator of kernel of theta, and we define this A Cris as this series in which these coefficients go to 0. This is in the p-adic topology. This convergence is in the p-adic topology. So this is some kind of taking something similar to taking a PD structure, divided power structure. And yeah, this is we may prove that this is the p-adic completion of this WR subalgebra here. So inside of this, we can take the algebra generated by these elements. So this is just the divided powers of this generator of the kernel of theta. So this subalgebra is stable under the Galois action, and it's usually usually denoted like this, A0 Cris. And so A Cris, the one that I'm defining here, is just the p-adic completion of that, seen inside BDR plus. So actually we need to have an embedding there. So yeah, there are many details, algebraic details that one should check there. But yeah, I should remark here too that here we are talking about convergence in the DVR topology here. Yeah, I'm just remarking this because here AN should converge to 0 in the p-adic topology. Okay, yeah. So that's, just give me a second. That's A Cris. That's A Cris. It's inside the BDR plus. Sorry. I'm going to state some facts about that ring. Starting with this, we might have this composite, where the first arrow is just the inclusion that I was talking about in the previous slide. And the second arrow is the one induced by the theta q that we defined yesterday, and that we saw that it was surjective. So we have actually a composition here of an injective map and a surjective map. And the important fact here is that the image of this composition here inside CP is actually OCP. So one needs to check first that the image is inside the OCP, and then when we see this map from A-cris to OCP is actually surjective. So the image of this map is actually OCP. So I will give that as an exercise that we might discuss if you want. Sorry. Yeah, so if you remember yesterday, this was the uniformizer that we were taking in BDR+, which was defined to be this series. So I'm leaving this as an exercise, but actually that element is an element of A-cris when we see A-cris inside the BDR+. And moreover, if I take the p-1 power of t, that's in the ideal generated by p. It's a multiple of p inside the A-cris. Okay. Yeah, so that's an exercise. And something else that we might say about A-cris, it's if I take an element in the kernel of theta, which is also inside the A-cris, then its divided power, x to the n over n factorial, is actually an element of A-cris for all n. And in particular, the divided powers of t are in A-cris. Okay, so yeah, that's actually very important when we speak about crystalline representations or crystalline cohomology. So yeah, we need to define the PD envelope and these kind of things. We might talk about those things in the next lecture. So maybe we'll see the relationship with crystalline cohomology that some of you have asked about. And yeah, so these divided powers will be very important. They have to do, if you think about it for a second, they have to do with some kind of integral, right? When you integrate the function t to the n, you get something like this, t to the n plus 1 over some number. So if you want to have all the derivatives and the integrals, you should have some elements of this type. So the story goes something like that. So of course, I'm not being very, very precise with those things. Yeah. Okay. So now we define this ring B-cris plus to be this one right here. So we want to invert P, and this is inside B the RAM plus. And B-cris is just going to be inverting T inside B-cris plus. Give me a second. Yeah. Okay. So we have this, the V vectors of the residue field is inside the V vectors of the ring R, which is inside the A-cris. And so that gives us this, that the unramified extension K0, which is just this, it's the V vectors of K, excuse me. the bit vectors of K, inverting P, that's going to be inside the B crease. That's just because of the definition and because of this. And so we have this theorem that we have an injection of this tensor product of B crease with K over K0 inside the B DRAM. And that's actually GK invariant, okay? And yeah, okay, so if you remember when we defined B DRAM, we defined a filtration inside there. So we would like to have a filtration also in B crease. And the fact that we are B crease plus inside B DRAM plus gives us an idea, right? Because we use the filtration in B DRAM to define the filtration in B crease. So yeah, this is actually very natural, right? Where is it? Here. No. Yeah, so when we define the filtration in the Dieudonné module, we use that filtration. So here we are using it again. And as an exercise, you can check that actually B DRAM plus is inside the zeroth piece of the filtration or the zeroth term of the filtration. And this is actually a proper inclusion. So these are not equal. Mm-hmm. Okay. And yeah, so we would like to see also the GK invariance of B crease, just as we did for B DRAM. And in this case, it's actually K0. You remember for B DRAM, the GK invariance was K. Here is K0. Yeah, I'm not proving any of this. As I said yesterday, the notes of Olivier Brinon and Brian Conrad, those are very good reference to see all the details of the proofs of this. Here I'm just stating the facts so we can eventually see the geometric part. Yeah. Okay, so if you remember, so we started this construction because we didn't have a Frobenius in B DRAM. So what we are going to do now is to define the Frobenius in B crease, which is actually what the thing that I shouldn't say that we need. It's probably what we wanted from B crease, right? Because we didn't have that in B DRAM. So we are doing some kind of a smaller thing just in order to have the Frobenius. So probably the original Frobenius that we have in W of R with P inverted could not extend to all B DRAM, but maybe it could be extended to something smaller, which is actually just the case, happens to be the case. So in order to define the Frobenius in B crease, let's recall that A crease is the p-adic completion of this. So A0 crease, it was this one. So the W of our algebra generated by the divided powers of this generator of kernel. And the important property about A0 is that it's actually stable under the Frobenius. So here we do have a Frobenius. And it turns out to be that this is stable under that. And so that allows us to define the Frobenius on A Cris, right? Because this is just the p-adic completion. So yeah. And once that we have Frobenius on A Cris, here, of course, we have Frobenius on B plus Cris. So yeah, this proposition is the important part if we want to define Frobenius on B Cris. And a very interesting thing is that this Frobenius is injective on A Cris. And this is actually hard to prove. But something easier to prove that I'm leaving as an exercise actually is that if we apply this Frobenius to T, where T is the log of epsilon, it's like Mueller-Leaf of epsilon, that's actually just multiplying by P. And this property allows us to extend the Frobenius to B Cris. So now we have Frobenius on all B Cris. Originally we had it here, right? So this proposition tells me that I can induce Frobenius here, and so we can induce it here, and this exercise tells me that I can induce it here. So yeah, this is all very nice because we have the Frobenius in B Cris that is induced by the original Frobenius here, which was really the problem in B the RAM, that we couldn't extend the Frobenius here to all the ring. So at least for B Cris we can. And so we are going to call a B Cris admissible representation just a crystalline representation, okay? And I can do something very similar to what I did for the RAM representations, in which I defined the functor D the RAM. Now I'm going to define the functor decrease. So for a crystalline representation, I just take the GK invariance of this tensor product. So it's just the analogous definition. And of course, we can define a filtration here just in the same way that we did for D the RAM. Why? Because B Cris has a filtration itself. So if you remember, let me go back. I'm sorry if this is stressful for you. Just give me a second. My computer is slow. Here. So we define the filtration in the Dieudonné module D the RAM by using the filtration that we had on B the RAM. So when we have D Cris instead of D the RAM, we have the analogous situation. So here, basically we just change the RAM for Cris, right? And here we change the RAM for Cris. Here the filtration is a little different. Well, it's actually induced by this one, but it's not exactly just changing the RAM for Cris. But we can put here filtration of B Cris, and so that would be the filtration of on the Dieudonné module, this one. And this gives a functor crystalline representations to filtered vector spaces. But here's the interesting thing. Here's the important thing about this construction that we made. I mean, we made this construction in order to have Frobenius. So we might change the target category to be this one, which is filtered vector spaces with the action of a Frobenius phi or phi. So decrease is a functor that goes from this category to this other. Yeah. Okay, so let me state this important theorem, which is called the fundamental exact sequence. That tells me that I have these two exact sequence. So the elements in B-Cris in which Frobenius acts trivially can be seen, can be mapped to this quotient, and that's actually surjective. And if I take the zeroth piece of the filtration there, I can take actually the inverse of Frobenius, and that's actually surjective too. So this theorem is very useful to study the properties of the functors decrease and DST that I have not defined just yet. And it's also very useful for constructing what is called the Bloch-Kato exponential. Okay. Yeah. So now I should go to yes. Sorry. I think I put here the exponent by mistake. Sorry. Thank you, Olivier. He was telling me that it should be this -1 should be here. It's -1, not the exponent. Thank you. Okay, so now I'm going to define the BST, and I'm going to give a definition that I believe it's the simplest one, but it's probably not the best one. It's probably not the most useful. But in order to have a simple definition, I'm just going to define it like this. Yeah, so just before doing it, it should be a canonical extension of B-Cris endowed with compatible Frobenius and Galois action, and a filtration on this tensor product. So I start by defining BST plus just as this polynomial ring over B-Cris plus, and BST as the polynomial ring over B-Cris. So it's not, I mean, maybe you think it's a very dumb definition. Of course, the important thing would be to define the Frobenius and the Galois structures. But what I want to say is that maybe this is not the most common definition, because as I said, it's probably not the most useful one. I would say in a moment what's the other definition. But it turns out to be as isomorphic as a ring to this. The thing is that that isomorphism is not canonical. It's not canonical, and that makes things to work better in the other way. It would make everything more canonical, right? So yeah. So I would like to take the break right now. So just to leave this definition here. So we already have the definition of B the RAM. We already have the definition of B Cris, and we stated some properties of them. And now we have a new definition, which sounds not too complicated. But we will see in a moment. What's the other definition for BST? Okay. So yeah, let me stop for 10 minutes right now. Okay, so we continue with what we were saying. We were defining the ring of the period ring BST, and we defined it just as a polynomial ring over B Cris. And we should define the Frobenius structure and Galois structure on this ring, which is just very simple because we already have Frobenius and Galois structure on B Cris, right? So the action on BST should be the most natural one. Well, yeah, with Frobenius, we should do this. So if I take a polynomial, I apply the Frobenius in each coefficient, but I multiply by p to the power n. And the Galois action just sorry. I didn't write it correctly. I don't know what happened here. I think it was a copy paste. The Galois action is not like that. It's just give me a second. I will write it with my hand. Sorry about this. I will correct this in the when I I'll upload this to Zulip. Yeah. So this should be G applied to A N multiplying X plus I would say in a moment what this is. C of G multiplying T to the power N. So what is this C of G? Well, if I apply G to this P tilde that I was talking about earlier, this actually turns out to be P tilde multiplying power of epsilon. So that exponent of epsilon, that is C of G. So this is epsilon Yeah, I'm sorry about this. It was a copy paste that I didn't correct. Excuse me, were you looking at my screen when I wrote this?
Yes, yes, yes.
Okay, okay, because I got a message here that about that. Okay, so yeah, this would be the Galo action. Okay. Yeah, and here we are going to have a new thing that we didn't have before, which is monotony operator, which in this case is just minus derivative in the polynomial ring. And the big theorem is that they are related in this way. Okay, so monodromy and Frobenius. So they almost commute, except for a factor p. And yeah, so I have this map from this tensor product, BST to be the RAM, given in this way. So if I apply to, excuse me, to this simple tensor, this is just this. So P evaluated in log of this. That is injective. And yeah, so the remark is that this map is not canonical. So this is one of those problems that I was talking about of defining BST in this way. But it is GK equivariant. Yeah, so here I have the comment. I will give you the new definition in a moment. Just let me finish with this part. So we are going to define the filtration on BST. Just as we have a filtration on B the RAM and B Cris, we also have the filtration on BST, just induced again by B the RAM, okay? By the one in B the RAM. And the GK equivariance, I mean the GK invariance of BST is K0. Okay, so I will sketch how it goes, the alternate definition of BST. So just for you to know that this is probably a better definition. So first, sorry, there's an arrow missing here. We define some kind of logarithm morphism from the units of R to B Cris plus, which is GK invariant. And that induces a morphism from this symmetric. Actually here it should say, I mean, here we are actually taking our tensor product with Q, but we write like this just for simplicity. So sim Q of R times R cross, I mean this, okay? And so with this, so this gives a B Cris plus a structure of this thing algebra. So we define BST plus as this tensor product. So we take again, this is with Q. And we take the tensor product over this. Okay, so that would be BST plus. And we have a canonical GK equivariant morphism from this multiplicative group to this BST plus. That I'm going to denote like this, lambda ST. And then we can define BST just inverting T. And And the isomorphism of BST plus with this comes by choosing an element here that is not here. Okay, so yeah, so the choice of this element is that gives me the isomorphism. So it's not canonical. That's the point. So I am using this definition to have the Frobenius and the Galois action defined in this way and this way, and the monodromy operator in this way. So if we use the other definition, we would need to redefine those things in terms of this new definition. And I think that would be a good exercise to think about it. So having that definition and looking at this other definition of BST, how it would go to the definition of Frobenius, of monodromy, and of the Galois action in this. Okay, so now we can define semi-stable representations to be just BST admissible representations. Okay, so now we have four different period rings, right? We have B Hodge Theory that Rogelio defined in his course. We have B de Ram that I defined yesterday. And we have B Cris and BST that we defined today. So that gives us Hodge state representations, the Ram representations, crystalline representations, and semi-stable representations. So we wonder if there's a relationship, I mean, among all of them. So we will address that in a moment. Just for now, if you remember when we studied the Ram, well, I mean, in all cases, actually Rogelio talked about that in his course. In all cases, we defined the Dieudonné module. So we would like to see the Dieudonné module for BST. So the DST, which is just this, of course. So we can define a filtration on DST on this module because we have a filtration on BST, and that gives a functor from the category of semi-stable representations to filtered vector spaces. But if you remember, I'm sorry to go back again. Where is it? No, it was decrease. Here, we could change the category, the target category, thanks to the fact that the Dieudonné module here has more structure, has a Frobenius endomorphism. And in the case of DST, we don't have only Frobenius structure, but we also have monodromy. And so we might change also the category here. So in contrast to decrease, in the target category, we have Frobenius and we have monodromy. And the Frobenius and the monodromy, where is it? They are related in this way, okay? So we might take the category of filtered vector spaces with Frobenius and monodromy. Let's satisfy that condition, okay? And we are going to denote it like this. And so that functor is going to behave very well too. It's going to be faithful, exact, compatible with the tensor products and duals. Yeah, so again, the details of that of this theorem can be seen in the notes by Olivier Brinon and Brian Conrad. Maybe I should upload them to Zulip as well, just in case. And yeah, so we have this big theorem, which is really the answer to, well, a partial answer to the question that I asked just a few minutes ago. If there's a relationship between crystalline representations and semi-stable, well, yes, all crystalline representations are semi-stable. Okay. Moreover, if V is semi-stable and DST has trivial monodromy, I mean DST of V, then V is crystalline. Okay, so this is really nice, right? Because the monodromy appears in those cases in which the representation is not crystalline. And so we might wonder in which geometric situations we have the crystalline representations, in which geometric situations we have the semi-stable ones. So this comes, this has to do with the fact of a variety. I mean, when we think of étale cohomology, for example, p-adic étale cohomology, this has to do with the fact of good reduction, right? So Rogelio more or less mentioned what this was. Maybe in the next lecture we see some specific examples of this, for example, for K3 surfaces or something like that. But the thing is that when we don't have good reduction, we might have semi-stable reduction. So what is semi-stable reduction? So just let me, I think Rogelio mentioned it too. Just let me remind you what it is. So we have a variety over K that I'm going to denote xk. I'm going to put here spec of K. With a semi-stable model. So what is that? So we're going to have here something like this. So that is a curly X. And here we have the spec of ring of integers of K. And we have here the special phi that I'm going to denote by X small k. Okay. So the main characteristic of a semi-stable model is that étale locally, this is étale over spec of OK. So I'm going to write something like this. So locally, it's given by an equation of this type. Well, I'm going to minus pi, where pi is a uniformizer. So that would be semi-stable reduction. So crystalline representations normally come from this good reduction, and semi-stable representations appear in this semi-stable reduction case. And so what we are saying here is that the monodromy operator on DST in this case has to do with the fact, or it could have to do with the fact that the variety has good reduction or not, because this is actually a geometric question, right? If we have a semi-stable model, we wonder, does it have good reduction or not? So in some cases, that might be reduced to asking if this spatial fiber is smooth or not. But using this, we address the question in terms of monodromy, right? In terms of the representations. So yeah, so probably in the next lecture, we will see some examples of how this works. So I just wanted to point out why this theorem is actually very, very interesting, very, very important, actually. Yeah, and also we have a similar theorem for semi-stable representations compared to the RAM. So all semi-stable representations are the RAM. So these semi-stable representations are related to both crystalline and the RAM, right? So crystalline representations are semi-stable, and semi-stable representations are the RAM. And in the case of B being semi-stable, the injective map that we have here is an isomorphism. So actually the Dieudonné module in the semi-stable case behaves like this. So yeah. Okay, so far we have seen that all crystalline representations are semi-stable, right? Here. All semi-stable representations are the RAM, right? And all the RAM representations are Hodge Theory. And so we might ask ourselves if the converses are true. So the answer is that not in general, but there might be some cases in which actually the converse is true. So yeah, I think there are two things that we should discuss here. So one is if we could find an example of a Hodge state representation that is not the RAM, if we can find the RAM representation that is not semi-stable, if we can find a semi-stable representation that is not crystalline, and actually this last one might have to do with the geometric situation that I was talking about a minute ago, right? Because yeah, so the good reduction criteria that one usually obtains is that the variety has good reduction if the Talco homology is crystalline, for example, for curves, or for example for K3 surfaces. We also have a criterion like that. So if we have a variety with semi-stable reduction, for example, that doesn't have good reduction, then that would give us a semi-stable representation that is not crystalline. So we turn this question into a geometric one, right? Yeah, but I would like to make a couple of remarks here. So for example, a Hodge state representation of dimension 1 is always the RAM. That actually has to do with the cyclotomic character. And give me a second. And also a semi-stable representation of dimension 1 is crystalline. Okay, so we also have this in dimension 1. So actually that could help us to find an example of the RAM that is not semi-stable. So using the fact that semi-stable and crystalline are the same in dimension 1. So yeah, that might help us to find the RAM representation in dimension 1 that is not semi-stable. Yeah, but in general, all the converses are not true. So yeah, we can always find an example of Hodge state that is not the RAM, the RAM that is not semi-stable, a semi-stable that is not crystalline. So I think we will see that in the next lecture. So we will see the examples of this, and we will see also the geometry that is behind here, and that this actually has to do a lot with Jaime's course. I mean, well, more or less, because he was talking about this geometric situation in which you have how's it called, mixed Hodge structures, right? So in the complex case, the mixed Hodge structures appear naturally. For example, in the case of a family of varieties, so over the complex disk. So this is some kind of disk, right? Some kind of disk. This is some kind of disk without the origin, and this is some kind of the origin. And so here we are saying that in the classical complex case, we would be saying here that that the fibers outside the origin are smooth, and we wonder if the special fiber, we don't know if the special fiber is, maybe it has a local behavior of this type, right? And yeah, in those cases, as the cohomology comes with a mixed Hodge structure in a natural way. That's the article of, I forgot the name. It was the limit Hodge structures. The limit Hodge structure. I forgot the name of the author, but yeah. So what I'm trying to say here is that all of this p-adic Hodge theory helps us to study the p-adic version of the same geometric situations that classical Hodge theory studies in the complex case. Okay, so that's why I prefer to go in that direction for the following 2 lectures. So just to make the connection with all these other courses that we are having in this school, and we might discuss as well some recent results and some open problems. But I think that for defining the period rings, I think we can be happy with this. We could discuss some other details that they will probably appear, some other details about them. But from now on, we will focus more on the geometric part. And I think I should stop now. I'm sorry that it's early, but yeah, this is all for today.